My name is Graciela Bachu, and I was going to talk to you guys a little bit about the BB84 Quantum Cryptography Protocol. So before we begin, I just wanted to introduce myself. Like I said, I'm Graciela, and I wrote a literature review on the BB84 Quantum Cryptography Protocol. I'd like to thank my mentor, Dr. Naomi Nishimura, for all her help on the paper and throughout the entire process. She's been really great. So today I'm just going to go over a few different things. First, I'm going to talk a little bit about the background of my project. Then I'm going to talk a little bit about the actual protocol and how it works. After that, I'm going to talk about one attack on the BB84 protocol, and then I'll talk about some variations of this attack and some forms of reinforcement. So first, I'm going to go into a little bit of background because, as you might imagine, quantum cryptography is a really niche area, and a lot of people don't have too much background in that. So first, we're going to talk about cryptography, then quantum computing, and then quantum cryptography, which is kind of an intersection between those two fields. So a brief introduction, whether in theory or in practice, like regular computers, quantum computers will need to ensure the security of information transmitted between and processed on them. And for those of you who don't know, quantum computers are used to solve really difficult problems that require a lot of computational power beyond what our regular laptops might have. So, your laptop might get overheated just running a couple of different programs, but these computers are designed almost like supercomputers to be able to process thousands of data points all at once and hopefully not take too long. So cryptography, a subset of cybersecurity with a heavy mathematical foundation, is used in current computers to keep our information safe. And for the same function, quantum computers would instead employ quantum cryptography, which is comparable to classical cryptography, but more deeply rooted in physics, specifically quantum mechanics. So a little bit of background on cryptography. Cryptography, roughly translated from its Greek roots, means secret writing. And the ultimate function of cryptography is to enable secure communications. And the way it does this is by making data indiscernible or inaccessible to all except the intended recipient. Some vocabulary to be aware of going forward are encryption, which means modifying a message to produce an incomprehensible ciphertext, decryption, the opposite of encryption, which means revealing the original message from the ciphertext by using a key, and ciphers, which are methods for encrypting and decrypting messages. Alice, Bob, and Eve are the message sender, recipient, and eavesdropper/adversary, respectively. So a little bit about ciphers. Historically, there were early physical examples of ciphers like the Cytail cipher and the Caesar cipher. The Cytail cipher was essentially you would write some letters on a little bit of a string of paper, and you would wrap it around a stick of a certain diameter, and that would give you the message, because otherwise you could just see kind of like a vertical column of letters. So that's one way a message was encrypted very early on. But cryptography started to get more mechanized around World War II, with one of the earliest forms of mechanized cryptography being the Enigma machine used in Nazi Germany. Now, modern cryptography is almost entirely digital and used on an exponentially larger scale than these past examples. Some times that you might be employing cryptography is when you purchase items online, send or receive a message, can connect to a site, or do any number of things on the internet. So cryptography is very prominent in our modern society. Quantum computing, on the other hand, is a relatively new field, with the first quantum computer being built in 1998. Quantum superposition is one of the ways that quantum computing differs from traditional computing. Quantum superposition allows for exponentially greater computational power than a traditional computer would have. And these quantum computers are able to do this because they use qubits or quantum bits, whereas traditional computers use classical bits. And these quantum bits are able to simultaneously represent a number of different values between 1 or 0, instead of simply denoting either 1 or 0 like a traditional computer bit. So quantum cryptography can be seen as the marriage between these two, quantum computing and cryptography. And we still have to use a shared key to encrypt and decrypt our data, though. Here, however, this key is constructed using photons. And these photons are subatomic particles, which is where the physics part of this comes in. We encode a series of bit values in these photons to a shared secret key to encrypt and decrypt messages or data, anything else that we might need, in a field of quantum cryptography known as quantum key distribution. The BB84 protocol is generally accepted as unconditionally secure. And when we say unconditionally secure, we're talking about theoretical security against an adversary with unlimited computational power. Computational security, on the other hand, is how our actual current algorithms and encryption schemes are defined by computational security, which means that an adversary with reasonable limits on computational power, like storage space, processing time, and different things like that, shouldn't be able to decrypt the message underlying the encryption that we already have. So in contrast to our traditional security algorithms, the BB84 protocol and other quantum cryptography methods would be considered unconditionally secure. So now that we've gotten through some background, let's go into what that protocol actually is and how it works. So a little bit of history. In 1984, Charles H. Bennett, an IBM researcher, and Gilles Brachard, a professor at University de Montreal, wrote a research paper called Quantum Cryptography, Public Key Distribution, and Coin Tossing, in which they proposed what came to be known as the BB84 protocol. An overview of the BB84 protocol is that it exploits the fundamental properties of quantum physics to allow users to generate a secure, shared secret key without ever announcing the actual key itself. This protocol calls for the use of polarized photons to transmit digital bits. These photons will be polarized in one of 4 non-orthogonal states, and in the original paper and in my lit review, they were 0 degrees, 45, 90, and 135 degrees, with one of 2 bases, either rectilinear or diagonal, as determined by the state, and one of 2 bit values, either 0 or 1, also as determined by the state. Down here, I have a visual representation of these polarized photons and the corresponding values that they would have. So as you might see here, with our first one, 0, the photon is polarized at 0 degrees, which means it's completely horizontal. There's no sort of tilt whatsoever in this visual representation of it. That means that its base is rectilinear. So if it's either horizontal or vertical, it's on a rectilinear base. And then the bit value it represents at this time is 0. And similarly, if the photon is polarized vertically or at 90 degrees, it's still on a rectilinear base, except now it represents the bit value of 1. You can see 45 degrees representing the bit value of 0 on the diagonal basis, and 135 representing the bit value of 1 on the diagonal basis as well. So there are 4 key steps for the BB84 protocol. First is encoding. So Alice, the sender that we discussed earlier, will randomly choose a bit, either a 1 or a 0, and a base to encode it in, either rectilinear or a diagonal. She'll repeat this step and sending a series of encoded bits as polarized photons to Bob, and noting the basis she used to encode each in the series. When Bob is receiving the bits, Bob will randomly measure each of them with either a rectilinear or diagonal base, noting the bases that he used to receive each bit value. And then in the reconciliation step, Bob and Alice will communicate on a classical channel to construct the same shared secret key. But obviously, this last step is going to be a little bit complicated. And the reason it is a little complicated is because of the Heisenberg uncertainty principle of quantum mechanics. So Bob must receive photons with the same base that they were encoded in to certainly receive the correct bit. The thing is, if Alice hypothetically sent a 0 encoded in the diagonal basis, which corresponds to 45 degrees, Bob would have to measure it with a diagonal filter also, meaning that if he measured it with a horizontal filter, he doesn't have an exact chance of getting the bit value sent by Alice. So he might get a 1 instead of a 0. So if he receives a photon with the wrong base, he's got a 0.5 chance of recording the wrong bit. This risk is due to the fact that the polarization of a photon changes when it passes through a filter that differs from the base that it was encoded in. So like I said earlier, if a photon is encoded as a 1 in a diagonal base, and you pass it through a horizontal filter, then it might come out as either a 1 or a 0, and you don't know if it was correct. This property of photons can be traced back to the Heisenberg uncertainty principle of quantum mechanics. In other words, it's the quantum part of quantum cryptography. So in terms of basis reconciliation, the fourth step, this is where you form the secret key. Because of the fact that Bob might make errors when choosing the bases, Bob will report the bases that he used to receive the photons, and then Alice will communicate which bases he selected correctly. Both will add the resulting bits from the correctly measured photons to their key, disregarding the bits resulting from the photons that Bob measured using the wrong bases. So now Alice and Bob should have the same secret key if all the bases that were added or all the photons that were added used the same bases. But just in case, Bob and Alice will usually verify. So to verify, Bob will reveal some of the bits in his secret key, and Alice will notify him whether or not they made any errors based on like whether or not they have the correct bit values. If they did, they would start over and try again. Then the bits revealed by Bob for verification would be removed in the case that they are having no errors. And then the remaining bits would be the final version of the shared secret key. So now that we've established how the protocol works, let's go through a brief attack, namely the full intercept resend attack and why it fails when executed against this protocol. So the concept here is basically Eve, the adversary or eavesdropper, acts as a Bob in between the real Alice and Bob, randomly selecting bases to measure photons in and resending those same photons to Bob after measurement so that he doesn't suspect anything. Recall though that in the absence of Eve, Bob only has a 50% chance of choosing the right base to measure/receive the photon with. In this instance, Eve will have the same half chance of either choosing the correct or incorrect base to measure a photon with. Over here, we have a little table or figure of these various outcomes. So the one all the way leftward, this leftward channel, I'm not sure if you can see my mouse, but hopefully you can. But the one that corresponds to outcome number 9 essentially is where Alice chooses the diagonal base for bit value 0, so basically polarized at 45 degrees. Then if Eve chooses to measure in a diagonal base, which is correct because it corresponds to Alice's diagonal base, Eve's resulting bit value will be 0. Then Bob has half a chance to either choose a rectilinear or diagonal base. If he chooses a diagonal base, then he also will get the bit value 0. And in similar patterns, basically Eve could be getting the wrong value and Bob could be getting the wrong value, or they could both be getting the correct one. Sometimes one of them may get the wrong one, sometimes one of them may get the correct one. So those different outcomes are mapped in this chart here. And in several of the outcomes, 4 out of the 9 outcomes that we have listed here, the bit values will not be added to the secret key because Bob chose the incorrect base. So during the basis reconciliation stage, Bob and Alice will decide, oh, this is the wrong base, so we're just not going to add that bit value to our key. So in that instance, Eve doesn't gain any sort of knowledge on the secret key whatsoever. In 5 out of the 9 outcomes, though, they do add the bit value to the secret key because Bob chose their same bases as Alice. So in these instances where they do add the bit value to the secret key, there are 3 outcomes where Alice and Bob will not detect Eve because Alice and Bob both got the same bit value. So since there's no error, they can't detect that Eve was involved. However, in 2 of these outcomes, they will be able to detect Eve. And it might seem kind of small, like 2 out of 9, but the fact is that they're adding, out of the 5 times that they do add the bit value to the secret key, 2 of those times they'll be able to detect Eve. And with the string of a lot of bit values and a lot of photons, which is generally how secret keys are constructed, there would be about a 40% chance of them detecting Eve's presence in 1 bit. So for that reason, this strategy ultimately fails because it makes the attacker highly visible during the basis reconciliation stage. So let's go over some variations of this intercept resend attack and reinforcement against them. Obviously, I don't have too much time in this presentation, so I was just going to cover 5 simple ones that I kind of talked about a little bit in my paper, but just on a very basic level. There is something known as the naive intercept resend attack, and it's a little bit of a watered down version of the full intercept resend attack that we just covered, and it's ultimately ineffective just like this one. Maybe not exactly for the same reasons, but also ineffective. The Breitbart basis intercept resend attack is also ineffective, with both of these resulting in an information gain value less than the ideal 0.5 information gain value that Eve has in the full intercept resend attack. Some other attacks include the Trojan horse, fake state, and middleman attacks. In the Trojan horse attack, Eve uses an intercept resend attack as part of this Trojan horse attack, and certain hardware can be used to detect and defend against this Trojan horse attack because the Trojan horse attack is essentially based on the hardware used to execute the BB84 protocol. For the fake states attack, this is a special form of the intercept resend attack, and depending on how the attack is executed, Bob may defend against the attack in a variety of ways, but it's a little complicated, so I don't have too much time to get into it here. And then in the man-in-the-middle attack, it uses the intercept resend attack, but the way that it can largely be solved is through authentication methods to add another layer of security to the BB84 protocol. So that's all I have for today. And if you guys have any questions, feel free to